A company called NWAC Electronics manufactures simple cables for a defense contractor. Each cable must go through four sequential operations, that is, splicing, soldering, sleeving, and inspection. There are also four types of cables that they should purchase. There is SC320 and SC325, and there's also SC340 and SC370. So here we want to help them to solve their problems. So here's are the problems.
For the first problem, formulate the problem as a linear programming model and determine the optimal protection schedule. Okay, in this segment, we will dive into part A of the NWAC case. Let's break it down. So, let the decision variables be defined as follows. X1 as number of units of cable SC320 to produce. X2 is the number of units of cables SC325 to produce. S3 is the number of units of cable SC340 to produce. And X4 is the number of units of cable SC370 to produce. And we have objective function. There is like this. And also we have 8 constraints. There is splicing capacity, soldering capacity, sleeving capacity, and inspection capacity. And also we have a minimum production constraint. There is X1 greater than or equal to 100, X2 greater than or equal to 100, X3 greater than or equal to 100, and X4 greater than or equal to 100. So we have a new mathematical model with a slack variable and also 4 dummy variable. And we also have 8 constraints, and we also want to make the table of the model, mathematical model. Okay, in the first iteration, we have S1, S2, S3, S4, A1, A2, A3, and A4 as the basic in the table. And we choose the cell in column X2 and row A2, there is 1 as 0. Then we do row transformation like this. We will repeat these iterations up to 7 iterations. And this is the second iteration. This is the third iteration. This is the fourth iteration. This is the fifth iteration. This is the sixth iteration. And this is the last iteration. From the basis of 7th iteration, we obtain X1, X2, X4 equal to 100 and X3 equal to 138.42. Substitute X1, X2, X3, and X4 into objective function. Hence, the maximum total revenue
$4,011.16.
So this is the calculation using POM-QM, and we can see in the solutions that X1, X2, X4 equal to 100 and X3 equal to 138.42, and Z maximum in the POM-QM table is 4011.16. So manual calculation and the calculation using the POM-QM are the same.
And the second question, based on the dual prices, Do you recommend increasing the daily capacity of any of the four operations? Explain. In this problem, NWAC Electronics produces four types of cables. Each cable must go through four production processes: splicing, soldering, sleeving, and inspection. Each process has daily time capacity, and the company wants to maximize the total revenue while still producing at least 100 units of each cable type. This situation is first modeled using a primal program or a simplex method. In the primal, the decision variable represents how many units of each cable type to produce, and the constraint represents the daily time capacity for each process. However, in this case, we are not just asked to find how many units to produce, but we are specifically asked, should we increase the daily time capacity for any process? If yes, which one will actually increase the revenue? To answer the question, we need to use dual model. Why use dual model? This question are not talking about how many cables to make, but they are talking about how valuable its time capacity is. In other words, we are asked, if we increase splicing or soldering time by 1 minute, will that help the company earn more money? This type of question are answered by the dual model. In the dual, its constraint in the primal becomes a decision variable, and its decision variable in the primal becomes a constraint. This transformation allows us to measure the value of its constraint and especially time constraints. Since the primal model has a constraint function, so the dual model will have a decision variable. Let the decision variable be defined as, and this is the dual objective function. In this model, Y1 until Y4 represent the shadow prices of splicing, soldering, cleaning, and inspection time. That means we only focus on Y1 until Y4 because they are directly linked to the operation time constant. Y5 until Y8 represent the shadow prices of the minimum production constraints, reflect the importance of meeting the minimum production levels. So, in this case, we simply ignore Y5 until Y8. Therefore, the optimal dual values can be directly observed from the final primal table. You can see here. And as a result, we know that Y1, Y3, and Y4 is equal to 0. The shadow prices for these three operations are all 0, which means that increasing their daily time capacity will not contribute to increase in total revenue. And Y2 is equal to 0.4944. The soldering operation Y2 has a positive shadow price. This clearly tells us each additional minutes of soldering daily time capacity will increase total revenue by approximately 0.4944. Therefore, we recommend NWAC Electronics increase soldering time allocation to generate additional revenue.
The method used to find the dual of POM-QM is the same as the method used to find the simplex methods. We can analyze data table, which also lists the results of simplex methods and also contains the dual value results. We can see in the table there is the dual price results. For splicing is 0, for soldering is 0.49, and for sleeving is 0, and for inspection is 0. So, the final result is the same as using manual calculation.
Do the minimum production requirement for the four cables represent an advantage or a disadvantage for NWAC Electronics? Provide an explanation based on the dual price or Simplex.
We can see in the table that there are dual price for 4 cables and all dual values are negative except for LC340. Dual price for LC320 is negative 0.68. For LC325 is negative 1.36. For LC340 is 0 and for LC370 is negative 5.3.
Fact that the shadow price and the lower bounds on X1, X2, and X4 are negative, show that the lower bounds on have adverse effect on profitability. So, if NWAC Electronics product Y5 greater than equal 100, it will reduce revenue by $0.68, as well as for cable Y6 and Y8, which will reduce revenue if greater than equal to 100 by $1.36 and $5.30. Specifically, one unit decrease in the production of cables Y5, Y6, and Y8 will respectively increase the profit by $0.68, $1.36, and $5.30 per cables. These values are valid considering the cables one at a time. This is the table of cable shadow price and interpretation. So, whether minimum production for the four cables is advantage or disadvantage. For Y7, SC340 is a neutral and does not affect, while for Y5, LC320 and Y6, LC325 and Y8, LC370, it's reduced income, which can be seen to be disadvantage if there are production restriction on cable LC370.
Okay, our last problem, how would a 5% increase in soldering capacity affect the overall total revenue for NWAC Electronics? So for solve this problem, instead of calculating our new maximum revenue from the very beginning, we can just use the concept of sensitivity. If our new capacity of soldering time is still in the range of the sensitivity of our old soldering time capacity. And then, how can we determine the sensitivity of the two? Or here we call it as return of resources for soldering time. So the first step, we must note that the initial soldering time capacity is about 9,600, and then we increase it 5% on the soldering time, and it will be equal to 105% multiplied by 9,600, and it will be equal to 10,000. So the time soldering time capacity is 10,018 minutes per day. And then we must check whether this is still within the sensitivity range of the two. We have our random model in the right hand side value of the resources capacity like this. So the first row we have the capacity for splicing time, and then for the second row we have the capacity for soldering time, and so on. We have the column matrix like this. And after changing, we have the numbers in the matrix become like this. Actually, this is the same matrix as the previous one, but here we add 9,600 with alpha. And next, in order to maintain the optimal solution, namely the variables included in the optimal program, that is x1, x2, x3, x1, s1, s3, s4, and s7, following pathway. So in our previous calculation, we have obtained several variables that are in our optimal table. x1, x2, x3, x4, s1, s3, s4, and s7. So that we can maintain the optimal solution, we have fulfilled this inequality. So the inverse matrix of the column value of the variable in optimum table in the first table must be greater than or equal to 0 when we multiply it with the resources capacity matrix. Solving this, we will get the value of alpha. The first one, alpha must less than or equal to 601.68, and alpha must greater than or equal to minus 618, and alpha must be less than or equal to 15,151.5, and alpha must be less than or equal to 8,169.6. Thus, we got the value of alpha must be between minus 608 and 601.68, which is equals, which B2 is mass in the range 8,920 and 10,201.68. And the final soldering time capacity, that is 10,080, is still within the range of B2. And next, we will calculate the maximum Z with the new capacity for soldering with the concept of sensitivity. Here, we multiply the inverse matrix of the column value of the variable on the optimum table in the first initial table with our matrix of capacity of operations. By help of Excel, we get the value of x1, x3, and so on. And next, we obtain x1, x2, x3 equals to 100. And here we obtain x3 equal to 165.54. And round the value of x3 downwards, we get x3 equals to 165. Thus, we get the Simplex by substituting our value of x1 and so on to the Z-mix formula. We get the value equals to 4,243.75. Hence, the maximum total revenue of Z is 4,243.75 and therefore a 5% increase in soldering time capacity resulted in an increase in revenue of $136.25. And actually, we can get the same value if we multiply the bulk price with the number of increases in soldering capacity time. Get the same value. 236.25.
The sensitivity itself is also based on the optimal table from the simplex method. We click the range button and we will get the sensitivity. Based on the results, the sensitivity is found in the soldering capacity, which ranges of 8,920 to 10,201.72. So, the final result is the same as using manual calculation.